This is the lecture on mass spectrometry. It's our final spectroscopy that we're going to talk about in terms of trying to figure out structure of our organic compounds. Mass spectrometry tells us the molar mass or the molecular weight of the species that we're looking at. In order to obtain a mass spectrum, you'll have your sample and then you have to ionize it. So there's a lot of different processes that we can ionize it, but ultimately what we're doing is we're kicking off an electron to make a positive radical, so a cation radical. Once we make that cation radical, it'll go into the mass analyzers. So that segment of the mass spectrometer, it's going to select for the proper mass that will go through into the detector, and then ultimately we see it displayed on a computer. A schematic of the spectrophotometer is shown here. We have the sample inlet, which goes into a heated filament area, and that is where the electron ionization happens. What happens with electron ionization is that we bombard our molecule with high energy electrons, and that's going to then kick off an electron. Then it gets carried into the instrument through a slit. The magnet is what selects for the mass that we want to go through. Ions that are too heavy or too light will get deflected onto the sides. The ions that we want, we use the magnet to get them to come right through the slit, right into the detector. There's a huge number of things that we can use mass spec for, ranging from pharmaceutical, biotech, clinical, and forensic. There's many more. This is a highly useful and highly used technique to look at identification and evaluation of the compounds that are in a mixture. So I said before, mass spectrometry, or MS, tells us the molecular weight of a compound. And this happens after we bombard our molecule with electrons that will ultimately remove an electron, again, to create that cation radical. Bonds in this cation radical begin to break. So we end up having our molecule fragment and break apart. And ultimately what we're looking at is the charge to mass ratio. So here's a schematic. We have our molecule. We kick off an electron. And so we end up with what you see here, a cation that is also a radical. And then, of course, we have that one free electron. So here, if we talk a little bit more about the radical cation, the mass of this radical cation is the same as the parent compound. Remember, the mass of an electron is negligible. It's about 1/2000 of a proton and or neutron. So when we form that radical cation, and we've only kicked off one electron before any fragmentation happens, we end up with the mass of our compound. And if this molecular ion remains intact, it is not only our molar mass of our compound, but it is known as the M+ peak, and it is also known as the parent ion. And this is going to be important because this peak in our mass spectrum is going to be the molar mass of our compound. The parent ion, the molecular ion, the M+ is the molecular weight of our compound. So now if we talk for a few minutes about interpreting mass spectra. Some instruments are so specialized that we get high resolution or more exact mass determination, all the way up to 0.0001 mass units. And so that really helps us decide what atoms are actually involved when the molecular weight seems ambiguous. For example, we have a molecular weight of 72. We could either have C5H12 or we could have C4H8O. Both of those molecules, when you do a quick calculation, turn out to have a molar mass of 72. However, using the exact masses from the periodic table to calculate the molecular weight, we see C5H12 is 72.0939 and the C4H8O is 72.0575. So using a high resolution mass spectrometer, we can actually distinguish between these two compounds, even though they both have a general molar mass of 72. So when we get a mass spectrum, we're going to get a plot. And on the x-axis is mass of the ions, and this is in mass to charge ratio. So the y-axis is the intensity of the signal. And this just basically tells us how much of this fragment is around, and ultimately tells us this fragment that is well represented is a stable carbocation. The two things that we're going to talk about in the mass spectrum specifically are the base peak, which is the biggest peak, the one that has the highest intensity, and the parent peak, or molecular ion, or M+, and we just talked about that. That's the molar mass. That is our intact molecule. So the base peak is the highest peak, and this one I always describe as the most stable carbocation. So the mass spectrum shows the relative abundance of each cation that was detected. The base peak is the tallest peak, and it is the most abundant fragment, and that means it is the most stable fragment. For methane, for example, the base peak is the parent ion. So if you look up methane, we have C plus 4 H's, so that's 16. So right here on the mass spectrum, we see the largest peak at 16. So our most stable fragment, our most stable ion, is the parent ion, or the M+. For most compounds, the M+ peak is not the base peak. The parent ion, for pentane, for example, fragments easily. So pentane, C5H12, has a molar mass of 72. So we see a nice mass to charge peak at 72, right over here on the right. And then we see loss of 15 that gets us to 57. And then we see loss of 29 from the 72 that gets us to 43. And so you see that the base peak is not the parent peak. In a few slides, we'll learn a little bit more how to interpret the mass spec, but here the base peak is 43. So our most stable fragment has a mass of 43. And as you start getting more comfortable with mass spec, you'll know that 43 is a CH3, CH2, CH2. And again, we'll talk a little bit more about that in a little bit. Now, not to be confused with the M+ peak, we do have something that's called an M+1 peak. And what this is the parent ion, the molar mass of the complete compound, plus 1. And this is because of the occurrence of carbon-13 in our molecule. So remember, carbon-13 is an isotope of carbon. It has one extra neutron. So the mass of that compound with the one carbon-13 incorporated is going to be 1 mass unit higher than the typical M+ peak. And because carbon-13 only has a natural abundance of about 1%, we see that the intensity of our M+1 peak is about 1% of the molecular ion. And so for methane, our mass is 16. We just talked about that. And so our M+1 is actually going to be 17. And so you see the peak at 17 is about 1% of the one at 16. So that is not our molecular ion, so do not be confused. It just means that there's carbons in our molecule and that we have some carbon-13 in the sample. The other thing I want to share with you is this M+2 peak. Again, this is the molecular ion plus 2. And so why is it plus 2? It's plus 2 because we have 2 elements on the periodic table who have natural isotopes that are 2 mass units higher. Chlorine is one of them. So chlorine has 2 abundant isotopes, Cl35, which has a natural abundance of about 76%, and Cl37, a natural abundance of 24%. And so the way we can identify that it's chlorine is the existence of a peak that is 2 mass units higher than our parent peak. So first identify the parent peak. In this molecule right here, it's going to be the one that's at 112 mass to charge ratio. We see that the M+2 peak at 114 is about 1/3 of the intensity of our M+ peak. And that tells us that we have chlorine. And if you look at bromine, because bromine has Br79 and Br81, right? So we're going to see the 2 M+2 peak, and they're about equal, 51% to 49%. So if you look at our spectrum here, we have the M+ peak, and then the M+2 peak is 2 away from that, and now we have those almost equally abundant. And so that's the way you tell bromine. Chlorine, you're going to see that the M+2 peak is about 1/3, and bromine, you're going to see that they're about equal. And so this is a real telltale sign that you have bromine or chlorine. You see this M+2 peak. Okay, so now if we turn our attention to fragmentation in mass spectrometry, let's look at methane. Methane produces a parent peak of M to Z ratio of 16. We've already talked about that. And now we do see fragments that are at 15 and 14. We break the bond between the carbon and hydrogen in one case, and then we break a second bond between a carbon and hydrogen, so that we have two hydrogens that break off, so our fragment then is 14. Now, if we continue to delve a little deeper into the idea of fragmentation, remember that we're going to break the weakest bond. We're going to break the bond that lets us form the most stable carbocation. And so often we can get lots of information from the way a molecule fragments in terms of what the structure was to begin with. And so remember, the positive charge is going to go to the fragment that can best be stabilized. So we really are looking at the most stable carbocation. For example, if you start with 2,2-dimethylpropane. If we break the weakest bond and lose 15 mass units, which would be a methyl group, a CH3, we are going to make a fragment that has a mass to charge ratio of 57, which is this tertiary carbocation. And so in that case, that is probably going to be our base peak because it is so stable. So if we look at the fragmentation pattern for hexane, it has a mass to charge ratio of 86, which is our parent ion. So our molar mass is 86, but it also has peaks at 71, 57, 43, and 29, as shown here. So our parent peak, or our M plus, is up here 86. Right there is our M plus 1, right? So don't get those two confused. And we see that we have this base peak right here at 57. So if we subtract 57 from 86, we get 29. And that means that the fragmentation that happened in order to observe this peak right here at 57 was loss of 29, which meant that CH3, CH2 fell off. And what we have left is our radical cation that is observed at 57. So this means that our most stable cation is going to be one that breaks a CH3, CH2 off. And the reason that we can think about that as being a base peak is that we could actually break it off this end, or we could break it off this end, giving us a mass of 57 as our base peak. We also observe a fragment here at 71 where we take off 15, which is a CH3. We also see a peak here at 43, which means that we actually lost 43. So we've lost 43 and we have 43. And so that just means that we've cut the molecule in half. For 1 point extra credit, email me and tell me why we only see one of the two fragments when we break this molecule in half. So you can see that we could fragment the molecule in a bunch of different ways, but the spectrum tells us which one is the most stable. And it turns out that the most stable one is going to be the one at 57. So I just wanted to quickly give you a little bit of insight into some functional groups that we can also see patterns happening in our mass spectrometry. So if we look at alcohols, we often have alpha cleavage, which means that the carbon that has our OH on it, that bond in between that carbon and the alpha carbon. So if this is the carbon on the alcohol, this would be the alpha carbon. And so it cleaves right there. The other thing that we very often see with alcohols is dehydration. And so in the mass spec, we will see loss of water, which is 18. And that's very common. So the ion that we're actually looking at becomes the alkene in this dehydration type reaction. But whenever we see loss of 18, that's going to indicate that we probably have an alcohol. If you look at mass spec of amines, again, we have that same kind of alpha cleavage. But I think something that's even more important to talk about amines or nitrogens in general is if you have an M plus peak that is odd, then it means that it has to have a nitrogen. And it has only a single nitrogen or an odd number of nitrogens. And so whenever you see an odd M plus peak, think nitrogen, think an odd number of nitrogens. That's definitely a telltale sign. If your molecule has 0 nitrogen atoms, we're going to have an even number. If it has an odd number of nitrogens, then we're going to have an odd number. And if we have an even number of nitrogens, that cancels back out and we end up with an even number again. Ketones and aldehydes, this is a little bit tricky and probably really beyond the scope of this class, but what happens with ketones or aldehydes is we have what's called the McLafferty rearrangement. And so we end up getting alpha cleavage with our ketones or aldehydes. So if we look at the mass spec of benzene, we see this big peak, the base peak at 78. And because benzene is so stable, we really don't get any kind of fragmentation pattern that's very clear. So benzene is definitely pretty stable the way it is, and it doesn't like to fragment. And we do see this base peak at 78. Okay, so there you have it, mass spectrometry. I'll be doing one more video where we actually go through and do some calculations of molar mass, and we also do some interpretation of spectra. So stay tuned for that.